Alright, so in this video I'm going to be explaining another important article about domain adaptation with this title: Lighter, Better, Faster Multi-Source Domain Adaptation with Gaussian Mixture Models and Optimal Transport. And this optimal transport is just another natural measure of domain shift. And the way we reduce that domain shift is just using, in this paper, is about optimal transport. For example, in previous videos, we used Gaussian mixture models for domain discovery. So this paper in 2024 is from France. In this paper, we tackle multi-source domain adaptation, a task in transfer learning, where one adapts multiple heterogeneous labeled source probability measures toward a different unlabeled target measure. We propose a novel framework based on optimal transport and Gaussian mixture models. So the advantages: the optimal transport, this word is optimal transport, between GMM, Gaussian mixture models, can be solved efficiently via linear programming. I have a playlist for linear programming and algorithms that have discussed several questions that can be solved by linear programming, mixed integer programming, and quadratic, many different ways. So the second advantage is that it provides a convenient model for supervised learning, especially classification, as components in the GMM can be associated with existing classes. Based on GMM optimal transport problem, we propose a novel technique for calculating barycenters of GMMs. So you see the overview of the proposed methods. Squares represent actual domains. Circles represent barycenters, and triangles represent learned measures. Blue and orange elements represent labeled and unlabeled measures respectively. In GMM-WBT, a labeled GMM is determined for the target domain by transporting the barycenter of sources. So we learn to express each domain as a barycenter of learned Gaussian mixture models. We call it atom through dictionary learning. And we cover the necessary background that, Gaussian mixture models, this is the density of Gaussian mixture models. And that we have a mean, and this C is the covariance matrix. So a GMM is a probability measure such that P theta can be a linear combination of P sub k. So we can determine parameters through this maximum likelihood. So we focus on the problem of classification. Given a feature space and some label space, the problem corresponds finding the correctly classified data. And we use this empirical risk minimization, and it is useful for domain adaptation theory. So one resorts to minimization of empirical risk, because we don't know the actual risk because we don't have the probability distribution, but we can always work on the empirical risk. So this optimal transport is a field of mathematics concerned with the displacement of math at least effort For example, when we have a distribution and another distribution, what is the cost that we go from this distribution to the other, from source to the target, for example? And then this Wasserstein distance, because we need a metric between probability distribution, probability measures associated with this optimal transport. So this is the Wasserstein distance between two probability measures, P and Q, where C here is a common choice. It could be the distance between points in P and points in Q. So the distance between individuals. So it says equation 4 is hard to solve in general. It has, but it has closed form. Fortunately, the closed form solution for Gaussian measures. So we can write the Wasserstein distance like this, very explicitly. So dataset dictionary learning is an optimal transport-based framework for expressing probability measures as barycenters of synthetic measures called atoms. The authors introduce atoms and barycentric coordinates such that each measure in MSDA is expressed as a Wasserstein barycenter. And there are some theorems. But in this paper, we consider supervised learning problems. It is necessary to equip the components of Gaussian mixture model with labels that represent the classes in the datasets. We propose doing so through a simple heuristic based on the law of total probabilities. Because this one corresponds to probability that x sub I comes from the case component of Gaussian mixture model. You see Gaussian mixture model here. We have different distributions, different centers, and this one comes from the case. What is the probability that it comes from, for example, the case component? Because it could come from the first component of, it could come from second, it could come because K could be anything. So if you fix K, condition and X, you can go through all the samples. What is the probability of each of our samples to be taken from each of these components? So when the mixtures P and Q are labeled, one needs to take into account the labels in the ground cost. So the following distance between Gaussian mixture models they propose this one. So the idea is that we want to find M and S and Y. So this is Gaussian mixture model optimal transport between B and PP sub C. Here we are updating the barycenter parameters. We have, because it has 3 parameters, M, S, and Y. So the intuition of this algorithm, the first one, is transforming the MSDA in a scenario into a single source one by first calculating Wasserstein barycenter of B. After this step, WBT solves a single source problem between B and Q sub T. Our second algorithm consists of parametric version of this reference. The idea is to replace the atoms by GMMs parameterized through theta p. So we are learning dictionary, and this is the second algorithm that we are evaluating the unsupervised loss on target here. But this one is the supervised loss on sources only. Finally, we project variables S and lambda. This picture is very interesting. This is a summary of GMM-WBT by transporting the parameters of barycenters of sources.